Hi dear students, in this presentation we will discuss an important theory related to the brittle fracture, that is the Griffith theory of brittle fracture. Okay, this is an important one as far as the university exam is concerned. Fracture stress depends upon the crack size and material property, and probably the material property depending is stiffness. So uh, what happens is, if we apply some stress on a material, if you some apply normal force on a material, it is inducing some stress on the material. Finally, if the stress is within above an allowed stress, what happens is the fracture will take place. So the first person to establish quantitative relationship between a fracture stress and these quantities, crack size and stiffness, was Griffith. So this person Griffith has tried to identify the relation between fracture stress and crack size and stiffness. So all these are related. He identified that the crack size, that is some cracks. I have already told, in most of the brittle fractures, the internal cracks are the acts as a stress concentrators, and from that cracks only the failure is happening. So or we can say the cracks will propagate through the material and finally it is coming emerging out of the surface. That is what is happening. So void spaces will be there, or cracks will be forming inside the material. So that crack, if enough energy it is having, then that cracks will usually propagate. So always for the propagation of the anything we require the energy. Without the energy it won't happen. So Griffith has identified which energy is actually causing this cracks, for the cracks to propagate. That is what is actually the basic idea of Griffith's theory. Okay, the first person to establish quantitative relationship between a fracture stress and these quantities, cracker size and stiffness, was Griffith, and he did it for brittle fracture or brittle solids, and is known as Griffith criterion for brittle fracture. Okay, so what he identified is usually known as Griffith criterion for brittle fracture, since he did it for brittle fracture. Okay, even though it is did for brittle fracture, finally it became the milestone for the identification of the other cracks other failures in other failures also, like ductile fracture also. Okay, so this is the basic theory. Let us consider a plate of thickness b, and a normal stress sigma is applied to the plate at its ends, and is in center of and in the center of the plate there is a crack characterized by the length 2a as shown in figure. Let E be the modulus of elasticity or Young's modulus of the material. You can see this one in here. This is the plate of having thickness B. This is the large plates having thickness B, and you can see within that material at the center we can characterize a oval shaped crack having dimension 2a. 2a is the dimension. If the cracks are at the surface, usually instead of 2a we will be taking the size of the crack as A only. So since it is moving towards both the direction, at the center the crack will propagate towards both the direction. That's why the dimension is taken as 2a. Anyway, if it is interior crack, the dimension is represented as 2a. Size of the crack is expressed in 2a. Or if the size of the interior crack is given, then we have to consider half of that as A. Okay. If it is surface crack, then the given value directly you can take it as A. So since I am considering here as internal crack, so the crack size I have specified it as 2a. So initially there is a crack of size 2a within that material, and I have applied a normal stress sigma at both end of this material, and the thickness of the material is B. Okay, and of course the modulus of elasticity is given as E. If sufficient stress is not there, crack will not propagate. See, initially there is the crack there itself, crack is there inside the material, but it will not fracture at all. The reason is the sufficient energy is not there. Even if we apply low stresses, then also there won't be any failure. So but as we increase the load or stress, what happens is at a particular point the failure will take place. So if sufficient stress is not there, crack will not propagate. So for propagation of the crack, some energy of the system is to be decreased. So even if even sufficient stress is not there, the crack is not propagating. Actually I have already told, the failure happens because of the propagation of this crack. Crack is initially at a smaller area. Here you can see. Now if we apply stronger force, what happens is high stress is applied. What happens is this crack starts to propagate and finally it will be coming out of the surface. That is what is known as fracture. അപ്പോൾ ഇപ്പോഴൊരു ഉള്ളിലൊരു വോയിഡ് പോലെയാണ് ഉണ്ടാവുക. അത് പിന്നെ എന്ത് ചെയ്യും, സ്ട്രെസ് ഒരു പർട്ടിക്കുലർ ലിമിറ്റിൽ കൂടുതൽ സ്ട്രെസ് അപ്ലൈ ചെയ്താൽ എന്ത് ചെയ്യും, ക്രാക്ക് കൂടി വരാൻ തുടങ്ങും. ഉള്ളിൽ കീറി വന്നിട്ട് ഫൈനലി എന്താ പുറത്തോട്ടേക്ക് നമുക്ക് കാണാൻ പറ്റില്ല. ഉള്ളിൽ കീറി വരുന്നത് നമുക്ക് കാണാൻ പറ്റില്ല. അത് പുറത്തെത്തി കീറിക്കഴിഞ്ഞാൽ മാത്രമേ നമുക്കത് ബ്രേക്ക് ആയി എന്നുള്ളത് അറിയാൻ പറ്റൂ. അതുകൊണ്ടാണ് അത് സഡൻ ക്രാക്കിംഗ് എന്ന് പറയുന്നത്, ബ്രിട്ടിൽ ഫ്രാക്ചറിന്. ഓക്കെ. Now, anyway, if the basic idea is propagation of the crack is only creating that fracture, that is sure. But for anything to propagate, some energy is required. So, some energy of the system is to be decreased for the propagation of the crack. So, Griffith has thought what would be that energy which is getting decreased. We know that some form of energy is to be decreased for other form of energy to increase. So here the crack propagation is taking place along the material, through the material. So for the propagation of that crack we require some energy. See, you will be thinking that the applied stress is actually caused that crack propagation. Of course it has some effect on this crack propagation, but if that is the sole effect of crack propagation, then by applying a very small stress also the crack should propagate. That is not happening. See, only after a particular limit only fracture is taking place. That means the applying of the stress alone is not the reason for the propagation of the crack. Okay, so there is some other reason also. Anyway, Griffith could see by his analysis that energy which is decreasing in case of crack propagation is the mechanical energy of the system. See, by doing experiment he had identified that actually the mechanical energy or the potential energy of the system is actually decreasing for the crack propagation. How much energy is decreasing, that is actually contributing for the propagation of the crack size. So driving force for the crack propagation is actually decrease in mechanical energy due to strain energy that we have provided because of this stress provided at both ends. Because of this stress, some strain energy is developed within the material because pulling effect will be there, that is actually contributing to the strain energy. And also external work, how much external work we are doing. These two are actually the contributors of the mechanical energy. So this mechanical energy is actually decreasing for the propagation of the crack. That how much energy is decreasing, that is actually contributing for the propagation of the crack. So I am considering two terms. One is, now let U0 is the mechanical energy of uncracked plates. See, I have already told before cracking also, see we are applying some stress. If fracture is not taking place, then that energy is there within that material. See, U0 is the mechanical energy of an uncracked plate. Plate did not crack because of the application of stress. Now we are gradually increasing stress. So now UA is the mechanical energy of the cracked plate. See, finally the cracking is taking place. So UA is the final mechanical energy of the cracked plate, and U0 is the initial mechanical energy of the plate before cracking. So I have already told this difference in mechanical energy is actually contributed for the cracking. So then change in mechanical energy due to the introduction of the crack can be written as delta U is change in energy. M stands for mechanical, equal to UA minus U0. This change in mechanical energy actually contributed for the fracture because of the introduction of the crack. Even if there was no crack, then definitely it won't break, but because of the crack, introduction of the crack only this happened. So by introduction of the crack, some mechanical energy has reduced. That change in mechanical energy has actually contributed for the breakdown. So delta UM equal to UA minus U0, and by experimental study he has identified that this change in mechanical energy is minus phi sigma square A square B by E, where phi is constant, sigma square is the stress that we have applied. In that stress breakage happened actually. A is the size of the crack. Here if it is internal crack, actually 2A is the size of the crack. Half of that we have taken, that is size of the crack. If it is external crack, then definitely the given value you can take it as A. So minus pi sigma square A square B by E. B is the width of the plate and E is the modulus of elasticity. This relation itself is a long derivation, so we are not deriving it here. Anyway, we can directly write it as, from the identification from the experiments conducted by Griffith, he has found out that delta UM, that change in mechanical energy, is equal to UA minus U0 equal to minus phi sigma square A square B by E. So negative sign in this equation, of course the mechanical energy is decreasing here, that's why that negative sign came. But if see this much change in mechanical energy actually caused for the breakdown, but there is some problem. See here, sigma, it is depending on sigma square. So with whatever small value of sigma is applied, then also fracture should take place, but that is not actually happening. So there is some other reason also. But if this alone is the driving force for the crack propagation, then at a lower stress also crack is supposed to propagate. But crack propagates only at a critical stress value. നമ്മളൊരു ചെറിയ സ്ട്രെസ് അപ്ലൈ ചെയ്യുമ്പോഴൊന്നും എന്ത് ചെയ്യുന്നില്ല, ക്രാക്ക് പ്രൊപ്പഗേറ്റ്, ക്രാക്ക് അങ്ങനെ അവിടെ നിൽക്കുകയാണ്. ഒരു ക്രിട്ടിക്കൽ സ്ട്രെസ് വാല്യൂ കഴിഞ്ഞാൽ മാത്രമേ എന്ത് സംഭവിക്കുന്നുള്ളൂ, ക്രാക്കിൻ്റെ പ്രൊപ്പഗേഷൻ നടക്കുന്നുള്ളൂ. അപ്പോൾ ഈ ഇക്വേഷൻ വെച്ചുള്ള മെക്കാനിക്കൽ എനർജി ചേഞ്ച് കൊണ്ട് മാത്രം എന്ത് സംഭവിക്കുന്നില്ല, ക്രാക്ക് പ്രൊപ്പഗേഷൻ സംഭവിക്കത്തില്ല. ബട്ട് ക്രാക്ക് പ്രൊപ്പഗേറ്റ് ചെയ്യാനുള്ള ബേസിക് റീസൺ ഈ മെക്കാനിക്കൽ എനർജി തന്നെയാണ്. ചേഞ്ച് ഇൻ മെക്കാനിക്കൽ എനർജി കൊണ്ടാണ് ക്രാക്ക് പ്രൊപ്പഗേറ്റ് ചെയ്യുന്നത്. പക്ഷേ ചെറിയ സ്ട്രെസ് കൊടുക്കുമ്പോൾ ആ ക്രാക്കിന് പ്രൊപ്പഗേറ്റ് ചെയ്യാനുള്ള എനർജി അതിന് കിട്ടുന്നില്ല. റീസൺ എന്താണെന്ന് വെച്ച് കഴിഞ്ഞാൽ വേറെ ഏതോ ഒരു ഫോം ഓഫ് എനർജി അതിന് എന്ത് ചെയ്യുന്നുണ്ട്, ബ്ലോക്ക് ചെയ്യുന്നുണ്ട്. അപ്പോൾ ആ എനർജീനെ ഓവർകം ചെയ്യേണ്ട അത്രയുള്ള മെക്കാനിക്കൽ എനർജി എപ്പോഴാണോ ഉണ്ടാവുന്നത് അപ്പോൾ മാത്രമാണ് ക്രാക്ക് പ്രൊപ്പഗേറ്റ് ചെയ്യുന്നത്. അതുവരെ എന്താണ്, വേറെ ഏതോ എനർജി ഈ ക്രാക്ക് പ്രൊപ്പഗേഷൻ ചെയ്യാനുള്ള മെക്കാനിക്കൽ എനർജീനെ ബാലൻസ് ചെയ്യാണ്. സി ഹിയർ ദ ചേഞ്ച് ഇൻ മെക്കാനിക്കൽ എനർജി ഈസ് ഹാവിങ് നെഗറ്റീവ് സൈൻ. സോ സം പോസിറ്റീവ് എനർജി ഈസ് ദർ വിത്തിൻ ദ മെറ്റീരിയൽ വിച്ച് ഈസ് ഹിൻഡറിങ് ദ ക്രാക്ക് പ്രൊപ്പഗേഷൻ. ഇവിടെ ഒരു നെഗറ്റീവ് എനർജി ഉണ്ടായിട്ടുണ്ട്, അതിന് ഒരു അത്ര തന്നെ പോസിറ്റീവ് എനർജി ഉണ്ട്, രണ്ടിന് നെറ്റ് എഫക്റ്റ് എന്താ 0 ആവും. അപ്പോൾ ആ എനർജി ഏതിന് കിട്ടില്ല, ക്രാക്കിന് കിട്ടില്ല. പക്ഷേ ഒരു ടൈം കഴിയുമ്പോൾ ഈ നെഗറ്റീവ് എനർജി കൂടുതലും ഈ വേറൊരു പോസിറ്റീവ് സെക്കൻഡറി പോസിറ്റീവ് എനർജി അതുണ്ട്, അത് കുറവാകുന്ന സമയത്ത് നെറ്റ് എനർജി എന്താ നെഗറ്റീവ് ആയാലും മെക്കാനിക്കൽ എനർജി 0 കൂടുതൽ വരുന്നൊരു കേസ് വരും. അങ്ങനെ വരുമ്പോൾ മാത്രമാണ് ആ എനർജി ഏതിന് കിട്ടുന്നത്, ക്രാക്സിന് കിട്ടുന്നത്. ഐ തിങ്ക് ദ ബേസിക് ഐഡിയ ഇസ് ക്ലിയർ ഫോർ യു. ഓക്കെ, the reason is by but crack propagates only at a critical stress value. The reason is by introducing a crack within the material, two new free surfaces are also created. ഞാൻ പറഞ്ഞു ഉള്ളിൽ ക്രാക്ക് വരുമ്പോൾ അതിൻ്റെ മുകളിലും താഴെയായിട്ട് എന്താണ് ഫ്രീ സർഫസസ് ക്രിയേറ്റ് ആണ്. ആക്ച്വലി ക്രാക്ക് എന്ന് പറഞ്ഞാൽ എന്താണ്, ഒരു വോയിഡ് പോലൊരു സംഭവമാണ്. അപ്പോൾ ഒരു രണ്ട് ഫ്രീ സർഫസ് ഉണ്ടാവും, അതിൻ്റെ ഇടയിലൊന്നും ഇല്ലല്ലോ. ക്രാക്ക് എന്ന് പറഞ്ഞാൽ അതാണല്ലോ, അതിൻ്റെ മുകളിലും താഴെ രണ്ട് ഫ്രീ സർഫസ് ഉണ്ടാവും. സോ when the crack is introduced, two free surfaces are also created. Every free surface is associated with a positive surface energy per unit area. ഓരോ ഫ്രീ സർഫസിൻ്റെ കൂടി എന്തുണ്ടാവും, പോസിറ്റീവ് സർഫസ് എനർജി പെർ യൂണിറ്റ് ഏരിയ. ആക്ച്വലി ദിസ് പോസിറ്റീവ് സർഫസ് എനർജി പെർ യൂണിറ്റ് ഏരിയ is nullifying this negative change in mechanical energy. Okay, so let gamma be the surface energy per unit area. ഈ ഗാമ എന്ന് പറയുന്നത് സർഫസ് എനർജി ഒരു യൂണിറ്റ് ഏരിയയിൽ ഡെവലപ്പ് ചെയ്യുന്ന സർഫസ് ഏരിയ ആണ് ഗാമ എന്ന് വിചാരിക്കുക. അങ്ങനെയാണെങ്കിൽ ടോട്ടൽ സർഫസ് എനർജി കിട്ടണമെങ്കിൽ എന്ത് ചെയ്താൽ മതി, രണ്ട് സർഫസിലാണ് ക്രാക്ക് ഉള്ളത്, ആ രണ്ട് സർഫസിൻ്റെ ഏരിയനെ കൊണ്ട് ഇതിനെ മൾട്ടിപ്ലൈ ചെയ്താൽ പോരെ. ഓക്കെ, പെർ യൂണിറ്റ് ഏരിയ ഓഫ് ദ ഫ്രാക്ചർ സർഫസ്. നൗ ഇൻക്രീസ് ഇൻ സർഫസ് എനർജി ഡെൽറ്റ എസ് by the introduction of the crack is given by delta u surface. S stands for surface energy. So delta u is equal to 2 into by 2. There are two surfaces, ഒന്ന് മുകളിൽ ഒന്ന് താഴെയായിട്ട്, ക്രാക്കിൻ്റെ മുകളിലത്തെ ഭാഗം താഴത്തെ ഭാഗം, രണ്ട് സർഫസ് ഉണ്ട്. ഇത് ക്രാക്കിൻ്റെ ഏരിയ ആണ്. എ ഇൻറ്റു ബി ഈസ് ഫോർ ഏരിയ ഓഫ് ദി A is 2a is the crack size actually, and b is the width. So 2a into b is the total area of one side of the crack into 2 total surface area into gamma. Gamma means surface area per unit area, surface energy per unit area. So total you will get the delta US surface energy. അതായത് ടോട്ടൽ ക്രാക്കിൻ്റെ ഒരു സർഫസിൻ്റെ ഏരിയ എന്ന് പറയുന്നത് 2a into b ആണ്. ക്രാക്കിൻ്റെ സൈസ് എന്താണ്, 2a ആണ്. ഇവിടെ ക്രാക്കിൻ്റെ സൈസ് 2a ആണ്, ഇവിടെ ഇങ്ങോട്ടേക്കുള്ള വിഡ്ത്ത് എത്രയാണ്, b ആണ്. ഇപ്പോൾ താഴത്തെ ഒരു ലെയറിൻ്റെ ഒരു റെക്റ്റാങ്കിൾ പോലെയുണ്ട്, അതിൻ്റെ ഏരിയ ആണ് 2a into b. അതങ്ങനത്തെ രണ്ട് മുകളിലും താഴെ രണ്ട് സർഫസ് ഉള്ളതുകൊണ്ട് 2 times വരും. ഓക്കെ, സോ ഇറ്റ് ഈസ് 2 into 2a into b. ദിസ് ഈസ് ഏരിയ ഓഫ് one side of the crack. Since two sides are there, 2 into 2a into b into gamma. ഇത് ടോട്ടൽ ഏരിയ കിട്ടി. ടോട്ടൽ ഏരിയനെ ഏരിയ എനർജി പെർ യൂണിറ്റ് ഏരിയ കൊണ്ട് മൾട്ടിപ്ലൈ ചെയ്താൽ ടോട്ടൽ എനർജി കിട്ടും. ഇപ്പോൾ 4a into b gamma, that is the equation to calculate, equation for delta US. Now total energy, see two types of energy are there. One is mechanical energy or change in potential energy, we can say because of that strain energy within that material or because of that applied stress. So that we have derived, the expression is minus 5 into sigma square a square b by e. Now here you have second form of energy, that is positive energy, because of the introduction of the crack, that is surface energy. So the expression is 4a into b gamma. Now total energy due to crack formation is ut, delta ut total will be equal to delta um plus delta us. So the total will be this much value, 5 sigma square a square b by e modulus of velocity plus 4a b gamma. Now the interesting thing is, if you plot these two energies in a particular graph, you can see it somewhere here, that is along the y-axis we are taking delta u. It can be delta um, delta us, whatever, delta ut, whatever it may be. And along x-axis we are actually taking the crack size A. So with respect to crack size, I am drawing these two energies. See, the surface energy is actually 4a b into gamma. It is directly proportional to a. 4 is constant, b is constant, gamma is constant, all are constant properties of material. Only thing varying is crack size a. So with respect to, it is linear dependency, only a term is there. So if you draw a graph constant into a, that means we will get a straight line. So it will be a straight line. So this is the graph for delta us. 2a into, actually it is 4a, not 2a. This is 4a. 4a beta gamma, b gamma, sorry, not beta, b gamma. And if you plot the second expression, that is delta um with respect to a, what happens is, in the expression for delta um, it is actually negative, so always it will be below that x line since it is negative, and it is depending on a square. See, square is coming, therefore it will vary parabolically. So you can see that lower green graph will be corresponding to delta um equal to minus 5 sigma square a square b by e. So now think about delta ut. Initially, see, since both are, initially this is having positive value or positive slope it is having, and since the delta um will have a, we can say it, since it varies parabolically, initially it won't have much variation. So at the lower values of a, you can see, if you add these two together, the delta us or surface energy will have more value than that of mechanical energy at the initial point. So always the total delta t, total energy of the system is initially increasing, but you can see after a particular point, since delta um is having parabolic variation, so it varies drastically after a particular limit. So it will, since delta us is having linear variation only, so at this point, at some point we can see that the delta us will be, delta um will be much higher that of delta us. So at that point the delta ut curve will start moving downward. Okay, so there is a maximum point up to which this delta ut will be positive. So from this point onwards, delta ut is becoming negative or shifting towards the delta um curve, that means negative side. So up to maximum point there will be a crack size corresponding to that maximum point where delta ut is positive, remains positive, is what is known as critical crack size, and it is marked as AC there. Okay, so cracks with a less than AC will not propagate. The reason is the total energy of the system up to that crack size AC is positive. So the system is having positive energy, the crack will not propagate. So see, what is actually happening, നമ്മൾ മെക്കാനിക്കൽ എനർജി കുറഞ്ഞു വന്നിട്ട് വേണം ക്രാക്കിന് പ്രൊപ്പഗേറ്റ് ചെയ്യാൻ. പക്ഷേ സർഫസ് എനർജി ഉള്ളത് കൊണ്ട് ആ മെക്കാനിക്കൽ എനർജി കുറയുന്നതിൻ്റെ സർഫസ് എനർജി ഉള്ളത് കൊണ്ട് പോസിറ്റീവ് സർഫസ് എനർജി എന്ത് ചെയ്യും, അതിനെ ബാലൻസ് ചെയ്യും. അപ്പോൾ ക്രാക്കിന് പ്രൊപ്പഗേറ്റ് ചെയ്യാൻ പറ്റില്ല. അപ്പോൾ എപ്പോഴാണോ ടോട്ടൽ എനർജി നെഗറ്റീവിലേക്ക് വരും, നെഗറ്റീവിൽ വരും മെക്കാനിക്കൽ എനർജിയുടെ സൈഡിലേക്ക് വരണം. അപ്പോൾ എപ്പോഴാണോ ടോട്ടൽ എനർജി നെഗറ്റീവ് ആവാൻ തുടങ്ങുന്നത്, അവിടുന്ന് അങ്ങോട്ടേക്ക് മാത്രമേ എന്ത് ചെയ്യുള്ളൂ, ക്രാക്ക് പ്രൊപ്പഗേറ്റ് ചെയ്യൂ. സോ ക്രാക്സ് വിത്ത് crack size A less than AC will not grow. Cracks with crack size A greater than AC will propagate. So this is the limiting condition. So if A is less than AC, crack will not propagate. If A is greater than AC, the crack will propagate. And what is that condition is decided is based on the total energy. So initially the delta US or surface energy is having more positive value than that of mechanical energy, but as time goes on, what happens is, as crack size is increased, what happens is at a particular limit the delta um value, negative value, is going to be much more compared to the delta us. So there is a balancing force. So at this A is equal to AC point, what happens is exactly delta us will be equal to that of the delta um. So after that, after to the right of AC, what happens is delta um value will be higher than that of the delta us. So this is the right explanation. At lower stresses, why crack is not propagating is Because of that crack introduction, some free surfaces are generated within the material. So some surface energy is being created which is having positive value. That positive surface energy is actually nullifying the negative energy decreased because of the mechanical energy. Okay, that's why crack is not getting any energy for the propagation. But once that critical size is reached, what happens is mechanical energy, negative energy created will be, or the energy decrease within the material is more than that of the energy created by that of surface energy. So at that time crack can absorb that extra energy or decrease in energy by the because of that mechanical energy within the material, and utilizing that energy crack can propagate. Okay, crack will propagate only with the expense of the system energy. Now from graph it is clear that the total energy is getting decreased only after a crack size called critical crack size AC. At that point delta ut is maximum at A is equal to AC. So cracks with lesser size than the critical crack size will not propagate from a given stress, and crack size having greater than that of AC definitely will propagate, and finally fracture will take place. Now we want to find an expression for the critical crack size, and from this graph itself we have seen that A equal to AC is at the point delta ut is maximum. See, at this point only delta ut value is maximum. So at the maximum point at the maximum point, if you differentiate with respect to the dependent variable, then it will be derivative will be equal to 0. That property we are utilizing here. So at A is equal to AC, what happens is delta ut by dou A should be equal to 0. See, that means dou by dou A of delta ut, actually delta expression for delta ut is sum of these two quantities, that is minus pi sigma square A square B by E, and for A beta gamma B gamma. So differentiate these two only. Here A square term is there, here only A term is there. Differentiation is very simple. Now on differentiating, what we will get is this term becomes pi pi sigma square constant, B is constant, E is constant, all are constant. So A square on differentiation will become 2A. Here B is constant, gamma is constant, 4 is also constant. On differentiation A becomes 1. So 4 into B into gamma will be remaining here. Here minus 5 sigma square 2A into B by E. So B and B will get cancelled. Since right side it is equal to 0. And here 2 is there, here 4 is there. 2 we can take from here. Here we will cancel 2. So the remaining is, if you simplify, you will get AC equal to 2E gamma by pi into sigma square. That is the final expression for the critical crack size. AC is equal to 2E gamma. 2 is constant, E is modulus of elasticity of the material, gamma is the surface energy per unit area, phi is constant, sigma is the normal stress applied. So for a particular stress value sigma applied, this much is the critical crack size. Okay, that is the expression for the crack size. Derivation is also required in this case. Now with that data we have acquired, we can draw a graph something like this. Critical crack size for fracture for a given stress. See, for a given particular stress sigma, this much is the AC value. If the stress is increased, that means here you can see some dependency also. AC is directly depending on the modulus of elasticity and surface energy, but inversely it's square of sigma, it is depending on square of sigma square. So you can see, if you plot a graph like this, you can see in y-axis I am taking critical crack size AC, and along the x-axis I am taking sigma. Then if the sigma value is less, that means AC value is going to be more, and if sigma value is increased, AC value is going to be decreased. That is a dependency. And since sigma square term is coming and parabolic variation will be there, so based on that I will get a graph something like this. So I am considering 2 points. See, for a constant sigma applied, I am considering a point somewhere here. The crack size is only this much. A is the crack size. So that means this point is within the safe region. There is no crack propagation with this applied stress if the crack size is A. Okay. If for the same applied stress, consider a crack size bigger than that of AC. See, this is that point. A greater than AC. This A is less than AC. AC is this point. See, this is the, for a അപ്ലൈഡ് സ്ട്രെസ് ദിസ് മച്ച് ഇസ് ഇതാണ് ഞാൻ അപ്ലൈ ചെയ്തിരിക്കുന്ന സ്ട്രെസ്. ഇതിന് കറസ്പോണ്ടിങ് ഈ ഗ്രാഫിൽ ടച്ച് ചെയ്തിട്ട് റൈറ്റിലേക്ക് എടുത്താൽ ഈ ക്രാക്ക് സൈസ് ആണ് ക്രിട്ടിക്കൽ ക്രാക്ക് സൈസ് എന്ന് പറയുന്നത്. ഇതിന് താഴെയുള്ളൊരു ക്രിട്ടിക്കൽ ക്രാക്ക് ഇതിന് താഴെയുള്ളൊരു ക്രാക്ക് സൈസ് ആണ് മെറ്റീരിയലിൻ്റെ ഉള്ളിലുള്ളതെങ്കിൽ എന്ത് സംഭവിക്കില്ല, ഈ സ്ട്രെസ് അപ്ലൈ ചെയ്താൽ ഫ്രാക്ചർ ഉണ്ടാവില്ല. പക്ഷേ അതിനേക്കാൾ ഈ എ സിനേക്കാൾ കൂടുതലൊരു ക്രാക്ക് ഓൾറെഡി മെറ്റീരിയലിൻ്റെ ഉള്ളിൽ ഉണ്ടെങ്കിൽ ഈ സ്ട്രെസ് അപ്ലൈ ചെയ്ത് കഴിഞ്ഞാൽ എന്ത് സംഭവിക്കും, ബ്രേക്കേജ് വിൽ ടേക്ക് പ്ലേസ്. സോ ദ ഏരിയ ബിലോ ദിസ് ഗ്രാഫ് ആക്ച്വലി ഷോസ് the safe region, or we can say it as stable crack. ഇത് പ്രഷർ വെസലൊക്കെ ആണെങ്കിൽ പ്രഷർ വെസലൊക്കെ ആണെന്ന് വിചാരിക്കുക, അങ്ങനെയാണെങ്കിൽ ബ്രേക്കേജ് ഉണ്ടാവില്ല. പക്ഷേ എന്തുണ്ടാവും, ക്രാക്ക് ഉള്ളതുകൊണ്ട് സംഭവിക്കും, ലീക്കേജ് സംഭവിക്കും. പക്ഷേ നേരെ മറിച്ച് ക്രാക്ക് സൈസ് എ സിനെക്കാട്ടും കൂടുതലുള്ളൊരു ഇതേ സ്ട്രെസ്സിൽ തന്നെ ക്രാക്ക് സൈസ് എ സിനെക്കാട്ടും കൂടുതലൊരു ക്രാക്ക് സൈസ് ആണെങ്കിൽ സംഭവിക്കും ഒറ്റയടിക്കത് ബേസ്റ്റ് പൊട്ടിപ്പോവും. സോ ദ റീജിയൻ എബവ് ദ ഗ്രാഫ് ഇറ്റ് ഈസ് അൺസേഫ് റീജിയൻ or unstable crack will take place. So this is the expression for AC, and this is the graph showing for a applied stress we can check whether the particular crack size is in safe or whether it is not safe, we can identify. Or by drawing for any stress applied, see for this particular stress you can see if the stress is applied, I want to find out the value of AC, then what I will do is I will draw a perpendicular from here that is touching this curve here, and from there I will take a horizontal line. This one will be the critical crack size for the higher stress applied. If the stress applied is lower, that means we will have a higher value for the AC. That we can conclude from directly from this equation. If stress is increasing means sigma square, that square term is becoming as a denominator, so the total term is going to be decreased. So this will have a decreased effect on AC. So if stress increases, AC decreases. That is what is directly obtained from the graph also. We can explain the same graph in another way also. See, instead of drawing same graph I have drawn here, the variation of the crack size with respect to sigma I have drawn, but here instead of AC I am talking about A only, crack size only. I want to identify the fracture stress for a particular crack size. Okay, I know the crack size and I want to identify how much is the maximum stress which I can apply on the material. In that case, if this is the crack size within the material that I know already, then I will draw a horizontal line. From there I will drop a perpendicular, then this much is the fracture stress. So if the stress applied is below this point, then material will be safe, there won't be any cracking. If the stress applied is greater than this sigma f value or fracture stress value, then definitely breakage will take place. So for the same crack size, if the point I am drawing here, then it is in the safe region. If I am marking a point somewhere here corresponding to this stress, then the material is in the unsafe region. So from the same equation AC equal to E gamma by phi sigma square, I can write the equation for the fracture stress sigma f equal to this I am taking to this side and AC is going to the other side. So 2 E gamma by phi into a all raised to 1 by 2 sigma square, so root is taken to the other side. So sigma f equal to 2 E gamma by pi a into all raised to 1 by 2, or root of this much value. That is Griffith's equation. This equation is called the Griffith's equation. So if I know the size of the crack, I can calculate the maximum stress or fracture stress, or up to what stress the material will withstand without any crack propagation. And if I know the critical crack size, then I can, from that equation I can identify what is the maximum stress which the material can withstand. Okay, anything is possible. So for a particular stress I can calculate AC value from this equation, and for a particular crack size I can calculate the sigma f value, fracture stress, from this equation. These are the application of these two equations. Now according to Griffith's criterion, the crack will propagate under a constant applied stress sigma if an incremental increase in crack length produces no change in the total energy of the system. See, നമ്മളൊരു ക്രാക്ക് പ്രൊഡ്യൂസ് ചെയ്ത് അതിൻ്റെ ലെങ്ത്ത്, ക്രാക്കിൻ്റെ ലെങ്ത്ത് ടോട്ടൽ എനർജിയിൽ ചേഞ്ച് ഒന്നും ഉണ്ടാക്കുന്നില്ലാത്തൊരു പോയിന്റ് അതിന് കറസ്പോണ്ടിങ് ആയിട്ടുള്ളതാണ്. അങ്ങനെ അതായാലും മാത്രമാണ് ക്രാക്ക് പ്രൊപ്പഗേഷൻ സ്റ്റാർട്ട് ചെയ്യും. Okay, that is the increased surface energy is compensated by decrease in elastic strain energy or mechanical energy of the system. See, by introducing a crack, actually we are increasing the surface energy because of the introduction of the crack. Surface energy is increased, but this is compensated by decrease in elastic strain energy or mechanical energy of the system. If these two are equal, then only the crack will start to propagate. Okay, once the mechanical energy is becoming more than that of the strain energy within the material, then only the crack will start propagate. That is a simple way. The Griffith theory states that the crack will propagate when the reduction in the potential energy that occurs due to the crack growth is greater than or equal to the increase in the surface energy due to the creation of the new surfaces. So this is explained clearly here. So this is the Griffith's theory, which states that a crack will propagate when a reduction in the potential energy due to the crack growth. If crack is growing, so I have already told, for the propagation of the crack, there should be some decrease in the energy, that is mechanical energy or potential energy is actually decreasing. So when it will start is the question. So when this decrease in the potential energy or mechanical energy is greater than or equal to the increase in the surface energy due to the creation of the new free surfaces, then only the crack will propagate. This theory is applicable for elastic material that fracture in a brittle fraction. So this theory is applicable only for the brittle material. So this is all about Griffith theory. The derivation of that equation is also important. Based on that equation, we can do some problem also. And I have mentioned this point also. See, cracks we will consider as two types. One is central crack and the other one is edge crack. If the cracks are at edge, then the length of that crack itself is taken as A. If the crack is at center, then usually half of that crack length is taken as A. So it is 2A. Half of that is A. So in problem, while doing problems and all, if it is given as central crack, then take the half of the dimension given as A. In case of edge crack, take the same dimension as that of crack as A. The edge crack of length A has the same fracture stress central crack of the length 2A. So both will have the same sigma F. So if you are talking about edge crack of length A will create the same sigma F that created by central crack of length 2A. A relatively large plate of glass is subject to a tensile stress of 40 megapascal. So stress is given directly here. Sigma is equal to 40 megapascal. If the specific surface energy of modulus elasticity of the material glass are 0.3 Newton per meter and 69 gigapascal. So gamma is given as 0.3 Newton per meter and modulus of velocity is 69 gigapascal respectively. Determine the maximum length of the surface flow that is possible without fracture. So AC we want to identify. So equation for AC is 2 into E gamma divided by pi into sigma square. That was the equation 2. E is given as 69 gigapascal. So 69 into 10 raised to 9. And gamma is given as 0.3 Newton meter. And pi into sigma square. Sigma is given as 40 megapascal. 40 into 10 raised to 6 mega. 10 raised to 6 is mega. Converting into pascal, it is 10 raised to 6 whole square. So finally, you will get 8.2 micrometer. That is the AC value, critical crack size. So if the crack size is more than that value, then definitely the crack propagation will take place, and finally the brittle fracture also will happen. Okay. Thank you.